It is section 5.2, Taylor series methods. Here we have a preliminary. We rewrite the initial value problem. Y prime is f over xy, y x0 is y sub 0. For the problem, a continuous approximation will not be obtained. Instead, approximations will be generated at various points called mesh points. Also, the computation should be terminated at some point, say capital T. So we'll try to find the mesh points in the interval from x0 to t. Okay, we choose uniform mesh with the size h. So here h is t minus x0 over capital NT for some integer positive. Here we name the mesh points xn. Xn is x0 plus nh as usual, and y sub n is the approximation of y at xn. Okay, now we'll see the simplest Taylor series method, the Euler method. We'll see here now the first step, then we'll apply this technique for later steps. In the first step, we'll try to find an approximation of y at x1 matching the first interval x0 to x1 using Taylor series expansion. Consider the Taylor series y at x1 is same as now y x0 plus h, which is expanded in this way. Now using here y x0 is y0, so that can be replaced, and y prime at x0 is same as f at x0 y0. So we replace this term and this term by using these two equations, and then now we ignore this portion. Then here we can get this equation, and y sub 1 is an approximation of the value y at x1. That is the idea of the Euler method. Now, for later steps, we can apply this idea recursively. For example, y at x2 is now expanded by Taylor series, and here we replace here y at x1 and y prime at x1 with y sub 1, and now f of x1 and y1. So we can get this approximation. Y sub 2 is y sub 1 plus the mesh size times f at x1, y1. In this way, we apply this technique recursively. We can summarize in this algorithm the Euler method solving the first order initial value problem is formulated as here. Y sub n plus 1 is y sub n plus h times f of xn yn. Okay, here we have a geometric interpretation. Geometrically, it is an approximation of the curve. Okay, that is the curve. Now, for example, to get y sub 1, that is y sub 1, we are using slope at left edge points and f of x0 and y0 and matching h distance to get here y sub 1. We don't know y at x1, so that when we try to match another step, then we are trying to use here the available by using the available approximation y sub 1, we try to measure the slope f at x1, y1, and match again h distance to get y sub 2, like that. So the Euler method is using left edge estimation of the slope. Okay? That is geometrically interpreted. Okay. Here we have algebraic interpretation of the Euler method. By using the fundamental theorem of calculus, in fact, that's part 1, the solution for the initial value problem can be implicitly formulated as in this equation. Y at x is y0 plus integral from x0 to x, and here y f of t and y of t and dt, t integration. We can easily check that that is the solution even though it is implicitly formulated. First we differentiate it, then y prime x, that will disappear, and then from the fundamental theorem of calculus we can see that there is now f of x and y of x. So that is the differentiation, and if we plug x0, then x0 to x0, that will disappear, and here the value must be y sub 0. So that this is the solution. Okay. Now, for the solution, when x is x1, this equation can be written in this way. Y at x1 is same as y0 plus the integration from x0 to x1 and the slope. Now, we try to approximate that one, the integrand, and using the left edge value. So that here, for the integral, and this one is approximated by using the left edge value. Then now this is constant, so that here it can be written in this way, x1 minus x0 and f of x0 and y0. So that by combining these two, we can get this one. And of course, this is approximation of the integral. And so we, in the algorithm, we note this term by y sub 1. That is now the algebraic interpretation of the method, Euler method. Okay. Okay, for the Euler method, we have here convergence analysis. We assume that f, the slope, satisfies the Lipschitz condition in the second variable, y variable, and that means that there is some positive number such that for arbitrary choice of y1 and y2, it satisfies this inequality. Then the Euler method is convergent more precisely here. Now, yn and y at xn, this true value, that is approximated value, is now bounded by here c over lambda h and this term. This portion is a bounded number. As you can see from the note here, that 1 plus lambda h n, that is now bounded by here quite easy portion. Capital NT is larger than or equal to n, so that it is true. And this term is bounded by that one. So it's only depending on here the x0 and terminal point and Lipschitz constant. So that no matter how you choose h, it doesn't matter. This value is always bounded. You can figure out this inequality in exercise 5.6. Some hint is given in the exercise problem. Okay, here we have a proof, but I'll not go through the proof. And if you are interested in it, then you may try to read yourself. Okay. Let's see this example. Consider this example, the problem. Y prime is y minus x cubed plus x plus 1 from 0 to 3, and y at 0 is 0.5. This problem is the example problem from Maple software. Okay. Now we'll choose step size, the measure size. H is 1 and quarter and 1/16, and try to get the solution. Here, red curve is the exact solution, and now the Euler method is producing the blue curve. When H is 1, it is here, and when the solution is increasing rapidly, then slower, and go down rapidly, then also down is slower, so that at the end, the Euler method produces larger value. Once H becomes 1/4, then yet the tendency is the same, is slower increasing, and when it go down, is slowly go down, but the error becomes smaller. And once H is 1/16, then again the same tendency with a smaller error. That's the property of the Euler method. Here, for the problem with H 1/16, we implement a code for the method. Okay, here we have Euler method along with Maple software. Yeah, that is now for given f and x0, and now b is the terminal point and number of points, and y0 and y, capital Y, will save the solution at the mesh points. Here h is defined, and t and w will be used in this iteration, n is from 1 to nx. W, the function value, is updated using here w plus, that will be yn plus 1, yn plus h times f of t and w. So that is now xn and yn in the mathematical formula. After that, we save updated value into the ODE, and for the next iteration, we increase the time by h. That's the Euler method. And here we define f, x0 is 0, and terminal point is 3, and y at x0 is 0.5, and we choose 48, the subintervals, which means that h is 1/16. And along with the ODE opened, and we call the function Euler. And so that after passing this line, that will be filled along with the function values at mesh points. And for comparison, the error analysis, we try to get the exact solution by using dsolve. And here, exact y is given here now. Okay. Now we measure maximum distance. That is about 0.39. So about 0.4 is the maximum error. From this figure and around there, the maximum error will be about 0.4. Okay, that's the end of part 1. We'll continue in the second part along with higher order Taylor methods. Thank you.